Welcome to the SAFECode e-learning course, Secure Memory Handling in C101. At the end of this course, you'll not only write more secure code yourself in C and C++, but you'll also be prepared to participate in code reviews and spot common mistakes in other people's code. Along the way, we'll look at a few common myths about the security of certain practices in programming C and C++. The primary audiences for this course are developers and anyone involved in activities like manual code audit or code peer review, such as quality engineers. Secondarily, understanding this material might be useful to quality managers or others who make prioritization decisions about bug deferrals or about the levels of resources to put behind certain security efforts in your project. This course will cover traditional string handling, arrays, and format strings. Additional material will be covered in future courses. Let's start with an explanation of what actually happens in memory when there's a buffer overflow. You can see in this slide a diagram of the stack. When the main function calls the copy function, it will write in the stack the value of the function parameter, in this case pointer to stir. Then it will write the address of the program flow where it has to return once the function is executed. Then it will write the address of the top of the stack before the function was called. When we enter copy function, 16 bytes are allocated for the buff array. We can see in the diagram that the stack grows from the top of the memory to the bottom of the memory. It's important to know that when we write values on the stack, they are written in the other way, from the top of the stack to the bottom of the stack, as shown in the diagram. Before calling the function, the large string array of size 256 was filled with A's. So copy function will copy, via stir copy, 256 bytes to a buffer, which has a size of 16 bytes. So we are copying more A's than the buffer buff can fit. This will cause an overflow of the buffer buff, and as a consequence, the rest of the A's will still be copied toward the bottom of the stack, overwriting the values of the stack's frame pointer, SFP, the return address, and so on. The return address will now have a value of 0x61616161, 0x61 being the hex value of A. Therefore, this type of vulnerability is commonly referred to as buffer overflow. Once copy function is finished, it will return the program flow to the address 066161616161, which is outside the program's address space, causing a segmentation violation. An attacker can take advantage of this situation to insert a return address pointing to a location in memory that contains malicious code prepared by the attacker, which subsequently will be executed. This means that a buffer overflow vulnerability enables an attacker to execute arbitrary code with the privileges of the user under which the vulnerable application is running, one of the worst outcomes of security vulnerabilities. Now let's talk about a potential cause of buffer overflows: basic string operations. We'll start this discussion where these discussions usually start, with stir copy. Stir copy is a function that is defined to copy data from the source buffer to the destination buffer until it runs into the null terminator in the source buffer. Unfortunately, there's nothing about this function that guarantees there's enough size in the destination buffer to receive all of that source data. And if there isn't, it overruns past the end of the destination buffer and starts to control other places in memory that are exploitable for the types of things we saw at the beginning of this course. The sort of word-of-mouth strategy that developers tend to learn about to replace stir copy is to use this function stern copy. This receives a third argument, the number of characters to pass. People often figure out that if you pass something like the size of the destination buffer, this function will end up copying potentially nulls all the way up to the end of the destination buffer. So some people will think it's a performance optimization to limit the copy to the length of the source as computed by strlen. Of course, if you think about it, this isn't going to work properly either, because in the situation where the source is larger than the destination, passing the size of the source as the third argument will still instruct this function to copy too much data. So the reluctant programmer in this attempt has switched from passing strlen of source to passing size of destination in an attempt to avoid overrunning destination. If you're a long-time user of stern copy, you're probably shouting at the monitor by now. No, that's not right. You don't use the size of destination. You pass size of destination -1 to leave room for the null terminator. And there's this idiom afterwards where you have to manually guarantee null termination, because stern copy doesn't perform the null termination itself. To reconcile all of these problems, you might even have more complicated variants that involve macros that figure out the minimum between the strlen of source and size of destination minus 1. Over the years, people have worked this out and have decided among themselves that this seems to be the correct answer, right? Well, you might be surprised to learn that, at least when it comes to the security team, Stern Copy is also on the same list of bad APIs that Stir Copy itself is on. To illustrate one of the reasons why that is so, we can use this example. Let's say we're taking some code where we're trying to confirm that an untrusted string doesn't end in .exe because that would signal an evil file attachment. So we might do some code like if path is not an evil file extension on the source buffer, and as long as it's not, we'll go ahead and copy that file path to our destination buffer using the idiom that everybody's learned. The problem with this code is that Stern Copy silently truncates the data in the event that the source buffer was longer than the destination buffer, and it's actually changing the meaning of the data silently in the process. It might take a file name that ends in .exe, .txt, and change it to .exe. So we don't like functions that silently truncate data. At this point, you might be thinking, well, great, now there's just no win, and you're trying to trick me because if I copy the entire source into the destination buffer, it's an overflow. If I copy any less, it's a silent truncation, and that's bad. So I'm betting you're probably going to tell me to rewrite all of my code using heap-allocated string objects in C++, right? Now, things aren't as black and white as you might think. If in new code you can clean things up in classes and get away from all the old-style dangerous C-style string handling, absolutely go for it. That would be great in new code, but we need to give you a strategy that works better with the traditional idioms of your old code bases that have more of a C focus. And so we want to consider functions that are a little bit more of a drop-in replacement for Stir Copy. One example that we're going to look at here is Stirl Copy. One of the reasons we like Stirl Copy better is because it's very well designed regarding being able to detect truncation with this two-line idiom here. You always pass size of destination as the third argument, and then wrap that in an if statement that compares the return of that to the same value, size of destination. If that evaluates to true, a truncation condition occurred, and you can jump to whatever code handles that. It avoids a number of the mistakes that we built up to over the last few slides. It avoids having to remember to subtract 1 from the size of the destination buffer in order to account for the null terminator. It avoids needing to remember to null terminate. It's guaranteed to produce null termination no matter what. Of course, even Stirl Copy can't save you if you pass the wrong number. If you pass something like strlen of source, you could still shoot yourself in the foot, just as we showed on a previous slide. But it just lowers the chance that you'll do that by making you do less math. And you should always be able to look at this code and say the third argument should clearly be size of destination. Now, in your code base, if you're building wrappers around string functions, then you have something like, let's say, my Stir Copy. Then go ahead and give yourself something like my Stirl Copy as well, and make sure that your implementation of that function has all the characteristics that we talk about here. Not just that it guarantees null termination, but that it has return semantics that are useful for the idiom shown on the slide. If this is not the case, you only have partial emulation of Stirl Copy. Stirl Copy is obtainable by BSD license, and so even if it's not available in your programming environment natively, you can drop in an implementation of it and have it. We've shown through the first few slides some oversimplified examples that make it very obvious where the flaw is. Now let's look at some real code and see how in practice these flaws can be slightly less obvious, but still actually occur in real code writing. In the case of this example, all that's important to know is that this code is trying to copy some data from the string into a destination buffer, this bit. You can see on the first line, this bit is declared statically to be maxMyKey+1 in length. This code uses one of the bad functions, the Stern Copy function, and there are a number of things wrong here. It doesn't include the idiomatic guarantee of null termination. There's no line 10 here that does that. But more importantly, it makes the exact mistake that we showed in a more obvious form earlier in this course. If you figure out what the effect of a line code like line 5 is, in the case where there's no quote, : in the source string, This while loop ends up computing the string length of the source buffer because it iterates up until it hits the null in the source buffer. So known chars in this bit end up being the same thing as string length of source, and my stern copy ends up being just like the example we showed, where we passed string length of source as the third argument. If the string is very long, it will happily overrun the buffer, this bit, which had been declared with a static size. What makes this code particularly tragic is that this number may end up being larger than max my key, which is to say larger than the size of this bit as it was declared. The developer considered this on lines 7 and 8 and performed those checks in a debug assert, which helps the developer be protected while running the debug build, but doesn't protect the customer since those compile away to nothing in a release build. Besides the debug asserts, the proper validation should be made before copying the string. It's important to remember that the my debug assert statements are debug code and won't have any effect on the release build. So far we've seen that at least avoiding stir copy can avoid some obvious problems, and avoiding functions like stern copy can avoid some slightly less obvious problems, corner cases involving non-null termination, for example. Still, none of these functions guarantees us that we won't have passed the wrong number as that third argument. Not even stirl copy guarantees that. So we still are in search of solutions to problems like that. If you have the opportunity to work at a higher level with something like a string class, there are solutions that could help you. And if you're on the Microsoft platform, there are some APIs to look into. Furthermore, there are helper headers that break builds when unsafe or banned APIs are used. Such headers assist in enforcing the usage of safe API calls. When you look at an API like sterncat, it needs to know how much space is left in the destination buffer, which means that over the course of repeated uses of string manipulation functions, you need to do some bookkeeping to keep track of how much space is left in that destination buffer. By comparison, stirlcat just needs to know the size of the destination buffer, and it can look in there and see how much data is already taking up how much space in the buffer. You can compare the two code listings on the slide and see that using stirlcat really makes your life a lot less complicated and reduces quite a few possible sources of programming errors in your code. Here's a good place to stop and address one common myth. Some people think that simply being off by one with a string manipulation, for example, using stern copy and the corner case where the null might get stomped on and the string might not be null terminated, couldn't be a big deal. Because how much damage could you do with one extra character in a buffer? And the issue isn't really that there's one extra character in the buffer. The issue is once the null terminator is gone. For example, imagine that the null terminator is gone after the word hello in this memory layout. Once the null terminator is gone, the effective value of var1 is no longer hello. It's hello followed by foo 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 foo. Any functions that make assumptions about the maximum length that var1 could possibly have, because var1 itself was a statically declared character array of certain size, those assumptions will now be broken. It's because if you use while loops or stir copy or something like that further down in your code, those loops will iterate past the end of var1 and run into var2. And you can end up with not just one extra byte of data where you weren't expecting it, but with as many bytes of data as it takes to run into the next available null somewhere in memory. We've mentioned that stircopy is a bad API. There's really a whole family of APIs that SAFECode member companies call the banned APIs. There are things like stircopy and sterncopy, and there are safer alternatives like stirlcopy or stircopy-s, which is part of the Microsoft SafeC runtime or CRT libraries. And if you're working on a code base or project with many wrapped string functions, you should look at your wrapped string functions and figure out what the safe alternative is in your environment. Likewise, with stircat and sterncat, there are safe alternatives, and the same with sprintf and so on. It's notable that snprintf isn't listed by name on the list of bad functions, but we'll see later on how it has some dangers of its own that we should be worried about. Let's start with a straightforward sprintf example. Sprintf, just like stircopy, doesn't make any guarantees that the source data it's copying is going to make it into the constraints of the destination buffer. Let's consider code, for example, from an internet high-score server for games, where players connect over the internet and upload their player names and their high scores. This code on the server has to do a sprintf of player:space, followed by the player's name. There's no guarantee in this code that the player's name won't have exceeded 256 characters and won't overflow the buffer in the sprintf. In this case, it's better to use snprintf instead of sprintf. snprintf handles the truncation and null termination of the string. The null byte is always included at the end of what is being written. Another option that is better for this example is the strcat function. Strcat handles the truncations, but we should include room for the null byte when calculating the size of the destination, or dest size. If dest string is longer than dest size, then the string won't be null terminated, as opposed to what happens with snprintf. We've shown with things like strcpy that there's a pretty straightforward one-for-one remediation strategy moving to some safer function like strcpy, and with sprintf, we're going to need to do some work as well. If there's a constant that specifies the player name max length, you're going to need to reference it in a fix that you make here. If there isn't a constant like that, and player names really aren't length limited in your game, consider pushing back on this at the specification level and making sure there is a specified maximum length to a player's name. Then you can use code like snprintf, where you pass the size of the destination buffer -1, and you actually use an approach very similar to the strcpy approach. Now, this is strongly preferred to assertions that sprintf can be rescued with things like field limiters, where you use %.255s. The reason we don't like field limiters with %.255s is that it's very difficult in a code review to catch these mistakes, because %.255s means something very different from %255s. You notice that in this case, the number 255 ends up having to be hard-coded into the format string, whereas in practice these things are probably going to live in constants or variables where you're not going to be able to put them into the format string as a field limiter. snprintf, by taking these constraints as a separate argument to the function, works better in conjunction with things like constants or other defined values. Now, in this code, the other thing is not only could we fix this with a function like snprintf, but let's use the least powerful and least dangerous function we need to get the job done. All this is really doing is concatenating player quote, colon, quote, space, and the player's name. So a much simpler function like strcat would get the job done without any of the risks associated with a function like snprintf. If you use strcat, you should be thinking about what happens in cases of truncation. If you're using snprintf, you have to think about truncation and null termination, because snprintf, just like strcpy, doesn't guarantee null termination. People who are good about remembering that strings might be longer than their available buffer size can sometimes let their guard down when it comes to numbers. For example, we see in this code that somebody had reviewed this code and decided that this statically declared buffer of buffer buff size 18 could fit any number and didn't need any additional input validation check, because even the max unsigned size of this number could fit in this buffer of this length. But what the reviewer of this code appears to have forgotten is that if this code were to be compiled on 64-bit platforms, then the maximum integer size would be much bigger, and the value when expressed in base 10 would be much longer, enough to go far past the buffer declared in this case. Using snprintf or strcat would have been a better solution and would have guaranteed that no overrun occurred, rather than being very clever and working things out off on the side in a comment. There are a lot of these. Check your organization's banned API list. We'd recommend that you follow it in new code. It takes no more effort to write new code using the more safe APIs than it does to continue doing things the old way. Please understand, we're not asking you to drop everything and rewrite every existing line of code in your codebase. We realize that would be unrealistic. But if you're touching an area of code anyway, and it's going to be regression tested anyway, it's basically free for you to stop and retrofit a strcpy into a safer string API as long as you're there. It's going to be regression tested anyway because you touched the code. Note that this is beyond just best practice. For certain groups at your organization, this might actually be a contractual obligation. And if this hasn't already affected you, it may just be a matter of time until it might in the future. So you're doing yourself a favor if you start to clean this code up now. It's not only a good idea for the safety of your code base, it might also save you a fire drill and a headache if you end up signing one of these agreements later. This is a good place to stop and talk about another common misunderstanding about security in C and C++. Now, we keep talking about these statically declared buffers on the stack, and people who know just enough about how buffers in the stack are exploited will sometimes tell me that buffers that are located on the heap can't be exploited. This stems from the fact that the exploitation technique that they're aware of that works in the stack doesn't work on the heap. Just because an exploitation technique that's tuned for the stack may not work on the heap, don't assume there are no exploitation techniques that work on heap-based allocations. It has actually been demonstrated time and time again that there are exploitation techniques for overflows that work against the heap as well as the stack. Generally speaking, if an attacker can read or write memory locations they're not supposed to, or corrupt memory in some way, you should treat that as bad because it's almost always shown to be exploitable. We discuss the unsafe string operations and their impact on the stack only because they are rather common. But keep in mind that also memory manipulating operations can lead to the same issues. Proving something isn't exploitable is a high-risk venture. It's expensive and low reward. The cost of being wrong is high. The cost of being right is that you get to keep doing this forever, as the code paths change from release to release. You get to keep re-auditing it and keep reproving to yourself that it's still not exploitable, that some other code path hasn't suddenly made this exploitable. And all it is reward-wise is saving you a few minutes early in your life cycle, when this code is going to be regression tested anyway. But if you look for the right opportunities to work on this, you can fix it nearly for free. The last sort of frequently asked question or myth we'll talk about is this. We also sometimes hear, well, wouldn't it be easier to just turn on this Visual C++ compiler switch GS rather than go around and fix up all this code? GS flag is an example of a security-related compiler flag specific to Visual Studio, adding stack smashing protection to your code. You should do some research and find out what other security-related flags your compilers and linkers offer. It isn't an either-or proposition between choosing to turn on GS and choosing to retrofit your code and switch to using safer functions in new code. GS is like a seatbelt. It can save you in certain cases, but it's possible to drive so recklessly that not even your seatbelt will save you. So you do both. You drive safely and you wear your seatbelt. Likewise, you use safe coding practices and you put on the /GS seatbelt. It is worth mentioning that /GS causes program termination in the case of buffer overflow. Now, this may have a security impact because it can lead to denial of service attacks. In addition to that, we highly recommend making use of modern static code analysis tools, most of which are capable of finding buffer overflows and other memory corruption-related issues. Let's change gears and talk about format strings. We mentioned sprintf before, and we said that it had these problems where it could overrun the size of the destination buffer. But let's consider this other function, fprintf. Consider a couple of lines of code trying to print some debug messages to a console or a log, and the programmer takes the line of input received from some file and is just trying to log that input so that she can do some fprintf debugging. What if that input line contains user-controlled data and has format string placeholders in it? Well, if it has stuff like %d in it, it'll just goof up your stack, because now fprintf will start eating additional arguments off the stack. The same behavior happens if there are more format string arguments supplied than string arguments. Because beside the format string there is not the same number of string arguments, printf reads memory from the stack. But worse, if that format string has things like %n in it, that actually tells the printf or fprintf function to start writing data back into locations in memory, representing things like how many bytes it has formatted so far. It's important to mention that %n is no longer supported by Visual C++. The makers of Visual C++ decided that the small value this functionality provided was not worth the security risks. This functionality has been shown, not just hypothetically but in real-world exploits, that it can be misused for the same malicious operations that are possible with a buffer overflow. It can be used to write an arbitrary location with arbitrary values, and in that way control a return pointer, for example, and result ultimately in arbitrary code execution on the victim's machine. This flaw has been particularly common in elements like web servers and FTP servers. Applications that maintain server-side log files have tried to use this shortcut. Therefore, you should avoid using fprintf or similar functions, where untrustworthy input, which might have contained format strings, is taken and passed directly in the argument parameters. An alternative way of reducing effects of an attack would be to just pass %s as your format string, because that will guarantee that the attacker-controlled data won't be interpreted as a format string. We've talked about strings that are really just arrays of characters. Let's switch gears a little and talk about arrays more generally. Here are examples of some instances where an attacker might control something on a line of code that has something to do with indexing into an array, sometimes for read and sometimes for write. Look at this slide and consider how hard it is to prove that a vulnerability is not exploitable. For example, you might assume that the last example on the slide is exploitable because it allows an attacker to write an arbitrary value to an arbitrary location in memory. Then when you think about it a little more, you might figure out ways to produce exploits using the third and fourth examples on the slide, even though an attacker couldn't control the value being written. And we'll talk about that in a moment. With this second example on the slide, where we read a value from an arbitrary location in memory, there are certain instances where that might be helpful to attackers as well. Maybe there is secret information in memory that the attacker is trying to read out, and maybe this variable ends up being dumped as part of an output image format in a file converter code, for example. So you can't be sure that the second line of code isn't exploitable either. You should always think defensively. Think input validation here. For example, in the first line of code, am I expecting this attacker-controlled character to be null? Would I goof up this 256-letter long path if an attacker dropped a null into the middle of it? And so on. Code owners should be thinking about and documenting and correcting the flow of untrusted data through their code base. With the exception of that first example, which is really just a case of needing input validation, all these other things had to do with indexing into an array. We think about this less often than we think about strings, and yet it's just as exploitable. An unauthorized read from an arbitrary location in memory that an attacker can control might allow the attacker to look around in memory and find passwords that live elsewhere in memory, or private keys, or secret numbers that the attacker needs to know in order to predict the sequence of something. So it's hard to say that it's not exploitable, and as we discussed, the cost of being wrong is very high. An unauthorized write to memory is very likely to be exploitable, even if the attacker cannot completely control the data that's being written here. Even a hard-coded letter B or null written to an attacker-controlled location of memory could change 1 byte of a return address to allow the attacker to redirect the flow of program code to some other location in memory, or could null out something like a password. In general, you want to validate that an array index that you're using in an array is greater than or equal to 0 and less than the max value for that array. Remember that in C, using negative values does not work from the right-hand side of the array. It actually walks off the left-hand side of the array and starts to walk into memory for some other variable in memory. This is a topic that will be covered separately in future courses. Perhaps the worst case you could imagine with array indexing gone wrong is if the array indexing is indexing into an array of function pointers. Here's an almost real code example. Imagine there's something like a font embedded in a PDF. And imagine that for different characters in that font, there are different types of characters, and different types of characters need different functions to process them. So you might read that this is character code 1 and index into an array of function pointers to invoke the processing for characters of type 1. You might read the next character from the font, read that it's a character of type 2, and index into a different function pointer in order to run that code. Well, if you're reading untrustworthy data, for example, a font embedded in a PDF, an attacker might put a completely unexpected number here, a very large number or negative number, and be able to index off the end of this function pointer array and point to any other location in memory as if it were a function pointer. This would be very straightforward to use to alter the control flow of the program, to jump to arbitrary instructions that the attacker wants run on the victim's machine. But even without resorting to function pointers, indexing into an array can still result in arbitrary code execution. And here's the bitmap example. Here is code for reading in the color index from a BMP file. This code supports up to 256 index colors. However, BMP files can declare less than 256. So as frequently happens in these binary file formats, there's a number that tells us how many records are about to come next in the file, and then a sequence of that many records. We have this for loop that reads the dot by color used variable to figure out how many colors are declared to be used in the file, and then tries to read subsequent bytes into an array declaring all the colors available in this file. Well, what if the file declares that it's going to use more than 256 colors? This for loop will happily iterate as many times as the file told it to. The loop of incrementing through the contents of the file and reading successive bytes into the end of this array will eventually walk off the end of the array and start to read bytes from the file into other locations in memory. It was quite a neat file. You could send somebody a BMP file that, when they opened it, a command shell started to listen on a port number on a machine, and attackers could telnet to that port number and issue shell commands to the victim's machine. Let's recap what we've covered today. We've demonstrated common mistakes when handling strings, arrays, and certain functions. We pointed out that some API calls are unsafe and should be replaced with their secure counterparts. It turns out that these insecure API functions assume that the specified parameters are safe to use. We demonstrated that this is not always the case, especially when user-supplied input gets processed without applying adequate sanitization. As a result, severe security flaws emerge. This lets us conclude that handling user input is dangerous, and some API methods should be avoided. All input should be treated as potentially evil, and adequate sanitization has to be applied. Furthermore, the secure API methods for handling input should be used instead of their insecure counterparts. Besides secure usage of the API, further mechanisms supporting secure code should be utilized. Compiler flags that introduce stack protection as well as header files that forbid the use of insecure API functions should be used to further increase the security of your application. Future courses will cover additional information about Unicode, as well as integer wraparound, and how that relates to things like malloc and uninitialized variables as well. Here we list a few links and resources that you might want to explore to improve your understanding of secure memory handling in C and C++, detailing C secure coding guidelines and banned function calls further. Thank you for taking this course.